is F R sine theta. We know the torque, the F is MA. So the MA R, but A is omega R, or alpha R, right? A is R, so this is M alpha R times R. And then we combine these and I get mr squared times alpha. Mr squared, that is the moment of inertia for a point particle. So that is I alpha. And so I have torque equals I alpha, which is the rotational equivalent of F equals ma. Torque is force, moment of inertia is mass, alpha is acceleration. Okay, that's true for each point particle. And then if I want to take this law for a rigid body, I'm just adding up all of the torques and all the moments of inertia of all the individual pieces. And this works for point particles and it works for rigid bodies as well. Well, thank you. Take that as a compliment.
Okay, new classroom. Also, the way that work is the change in kinetic energy. And we used to have that work was the integral of F dot dx. So now we translate that into Greek, and that's going to become tau d theta. So work is tau d theta. And remember, power was F dv dt, or dx dt. So it was Fv, right? The instantaneous power was Fv. And so now we're going to have tau omega is the instantaneous power. Okay. Again, we're just taking all this stuff from linear and translating it into Greek for this. And P is also, remember, F dx was work, so it was dw dt, but that's the same here, dw dt. And if you take the time derivative of this, theta is changing with respect to time, and so this is just work, dw dt, and it gives you tau omega. So let's take a look at our first example. We've got a lot of examples here. What we have is this type of situation. Here's the axis of rotation. This is a disk, and so this is a downward pull of 5 newtons. And this thing is 2.5 kilograms and a radius of 20 centimeters. Okay. And so now we want to know the angular acceleration of the disk. Well, tau equals I alpha. Right? So alpha is going to be tau over I. And what's the torque in this case? It's going to be F R cross F. So RF angle is 90 degrees, so we don't care. Sine theta is 1. And so this is going to be 5 times 0.2 over, and then I. So now we need the moment of inertia for a disk. That's why you need to know these. You can just recall them quickly. For a solid disk, it's 1/2 mr squared. The mass is 2.5 kilograms and 0.2 squared. And so now, let's see what happens. That cancels out with that. This can become, and this is 1/5. So 10 times 5 over 2.5. Like that. So you end up with 20. Okay, now we want to know the tangential acceleration at a point on the rim. This should be pretty simple, right? Because A tangential is just r alpha. So we take 20 radians per second squared and multiply it by 0.2 meters, and that gives us what, 4 meters per second squared. Yeah, that's right. So in this problem, we want to know what is the initial angular acceleration of the rod. And so again, for part A, we know that tau equals I alpha. And so alpha is tau over I. Tau is the torque, and the torque here is simply the pull of gravity on the center of mass of this rod. And so the force is mg, right? This is in terms of m, capital M, sorry. And the distance is L over 2. And then I. The moment of inertia, this is a rod about one of its ends, so this is 1/3 ml squared. And so this cancels out with this, one of these cancels out with one of these, and I'm left with 3 halves, 3 over 3g over 2l. Is that right? Yeah, 3g over 2l. Okay, and then part B. Now I want to know what is the tangential acceleration of the center of mass. So here, and they're talking about at that moment, in that initial moment. So that's going to be easy. It's just, A tan equals R alpha. So it's L over 2 times 3 over 2 G over L. Sorry, L over 2. So the L's cancel out. So I get 3 over 4G. And then C wants to know the tangential acceleration of a point on the right end. So we're talking about over here. So that's the same as this. We're just changing R to L. And so that is going to be R alpha. So it's L times 3 over 2 G over L. So the L's cancel out and we get 3 over 2 G. Surprising result that the acceleration of the right end is actually more than the acceleration due to gravity. It's kind of being, you think of it as being pulled through that distance by the center of mass here. And so the next one, the angular velocity of the rod when it is in its lowest point. And so here we can use conservation of energy. It's a GAPSI problem for this. And we can take the initial gravitational potential energy, and I'm going to set this as the data point. I'm looking at the center of mass. So this falls a distance L over 2. So this has potential energy mg L over 2. And then that's going to equal the final kinetic energy, which is 1/2 I omega squared. Okay, and then I can find omega F, when it's at this point by solving. And when we do the solving, we end up with something like this, that omega is equal to the square root of 3g over L. That's it. That's D. E, then the linear velocity of the center of mass, and then F, the linear velocity of the lowest point on the rod. So E, remember, V is R omega, so it's going to be root 3g over L times R, since we're talking about the center of mass, we're talking about L over 2, so times L over 2. And that can be simplified to 3/4 GL, square root of that. And then F, this is just going to be L times the square root of 3G over L. So again, I'm going to have the square root of 3 That's it. That's letter F. Okay, example 3 looks like this. Okay, for example 3, we have this type of setup. It's spinning around this axis here where the pin is. It's 2 meters long, which means it's only 1 meter to the center of mass. And it's released from rest. Determine the angular speed as it passes through the horizontal. So how fast is it going when it goes through here? Again, this is going to be a GAPC problem. And so I'm going to set this as my datum. And so what is the amount of potential energy that it has? Well, it has the mass of the rod, which we don't know, but it doesn't really matter anyway. So mg, and then what's this distance that it's falling? You know, from here to here, that would be 1 meter times sine of 40. So just sine 40. So mg sine of 40, this is mgh, right? So gravitational potential energy equals, again at the end, 1/2 I omega squared. Okay. And so I'm looking for omega. Again, so I'm going to solve this. Omega squared is going to be 2mg sine of 40 over, and the moment of inertia for this is 1/3 ml squared, right? 1/3 ml squared. So the masses cancel out. This is actually L over 2 in here. Well, this is 2. So one of these is going to cancel out with one of these guys. And so we've got still 2 on the bottom. So 3g sine of 40 over 2. And that's it. Then I take the square root. So omega is the square root of 3/2 g sine of 40. Okay. That's example 3. Okay. So for this one, we're told this is the force, and it has a radius of 0.1 meters. So now we can find the function of torque simply by multiplying these two things. So the torque is 0.1 times 0.5t plus 0.3t squared. Right, now I want to know the angular acceleration at a particular point in time. And so to do that, I can simply do tau equals I alpha. So alpha is going to be tau over I. Tau is this. And I is the moment of inertia of this thing. So that's 1/2 mr squared, right? It's a pulley. We can consider the pulley to be a, or actually, no, sorry, it just gives us, they just give us the moment of inertia, so we can plug that in. 1 times 10 to the negative third kilogram meter squared. So now all I have to do to get the angular acceleration at that time is to plug in 3 for t. So when you plug in 3, then what we end up with is 420 radians per second squared. But when I simplify this a little bit, what I find happening is that this becomes 50t plus 30t squared. That's actually going to be important. I'm going to need that for the next part of this, because I'm looking for the final angular velocity. Right? I want to know the angular speed at 3 seconds. So in order to get the angular speed, I can't use VIFTAT. I can't use delta omega equals acceleration times time. Instead, I have to do an integral. Okay, so here's part B, even though it's not labeled that way. So omega f minus omega I, but omega I is 0. So this is the integral of alpha dt. So from 0 to 3 seconds. So this is going to be from 0 to 3 seconds of 50t plus 30t squared dt. And so I get 50 over 2 t squared plus 30 over 3 t cubed. From, again, 0 to 3. So this is 25 times, I plug 3 into this, I get 9, plus this is 10 times 27. And so this ends up becoming 495 radians per second. Okay. For example 5, the main thing to see is simply that what the new formula we get, which is m2 minus m1 over m1 plus m2 plus I over r squared times g, that's the acceleration. What we see is that it's really very similar to what we had before, except that now we're just including a new mass here underneath. Right? It's the mass equivalent, we're going to call it. We're going to see that coming up again later. Okay. And that's the main point. So what if m1 is equal to m2? Right, question A. If m1 is equal to m2, then that means the acceleration is 0. Right? And that means that t1 equals t2, which is simply mg. Right? And if m1 is much, much greater than m2, then the acceleration is m2g over m2 plus I over r squared. So it's previously when we didn't have torque created by the pulley, this was just g. But now we still have that mass of the pulley that has to be spun around, so it doesn't just go to zero. Okay. And T2 will be 1 over r squared m2 over m2 plus I over r squared times g. See, if the mass of the pulley is 0, then we have the Atwood's machine. It's no different from what we had before. Okay. Example 6 highlights the importance of very carefully reading the problem, seeing what we're dealing with. This is a thin hoop. It's attached by a thin rod, and it's going to be rotating this way, okay, around this axis that's in the board. And all we want to know is the angular speed about the axis when it is inverted. This is a GAPSI problem. However, in order to do that, we have to find the moment of inertia. Calculating the moment of inertia of this thing is going to be challenging. And so we're taking one step at a time. The moment of inertia of this plus this, right? Now, we know the moment of inertia for a hoop, and this is r, right? And this is length 2r. So the moment of inertia for a hoop is simply mr squared. And so, but here's the thing, I'm not rotating this way. It's not turning. Instead, it's going around this way. So the first thing I have to do is actually use the plane figure theorem to figure out what's the moment of inertia for this to rotate this way, like into and out of the board. Well, the plane figure theorem works like this. If I have something like that, right? So here's x, y, and then z. So IZZ equals IXX plus IYY. IZZ is what this is. So this is mr squared. Because of the symmetry, the moment of inertia around this axis and this axis is the same. And so these two are equal to each other. So this is just 2IXX. So now I see the moment of inertia around this axis is 1/2 mr squared. And now I have to, so that's the moment of inertia around here. And now I still have to apply the parallel axis theorem because it's not going around this axis, now it's going around this axis. It's not turning this way, it's spinning this way, out and around. And this is the moment of inertia for a thin rod around one of its axes. So I total of this thing around this axis is going to be, it's 1/3 mr squared for the rod, so that's 1/3. It has a mass of m, and the length is 2r. Let's square that. And then I'm going to add this plus 1/2 mr squared. That's the moment of inertia of this around that axis. But now I have to apply the parallel axis theorem. This is 3r from this axis. So m 3r squared. Okay. And then we do some, I guess we won't simplify that quite yet. So now I'll write GAPSI. The total potential energy ahead of time, first is this. So the center of mass is there. And so this is mgr. This is the gravitational potential energy here. Right. Actually, this is going to fall 2r. By the time it's in its bottom position, this will have gone r and then 2r. So this is actually mg 2r. That's the gravitational potential energy of the rod. Plus, and then the gravitational potential energy of this, the center of this is going to fall a whole 6r, a distance of 6r. And so this is mg 6r equals 1/2 I, right? And this is I, this whole thing. So 1/3, actually we'll make this 4/3 mr squared plus 1/2 mr squared plus 9 mr squared omega squared. And omega is the thing that we're looking for in the end. After a lot of nasty algebra, and it's this. So now the physics is done. What you should get is omega equals the square root of 96 over 65 g over big R. That's it. So the tough physics here really, I think, is finding the moment of inertia and then setting up the Gapsy problem. Because you've got to apply first the plane figure theorem, then the parallel axis theorem and add up two things, and then figure out, okay, how far are these things falling to give us the amount of gravitational potential energy we have. Now in this problem, we're going to do what I know you've always wanted to do, right? Modified Atwood's machine with rotational inertia. We still haven't added in friction. But we have rotational inertia for the pulley now, and its radius r and moment of inertia I. Right? And so how are we going to find this? We want to know the acceleration of these things, and we want to know the tension in each of the strings. And because there is a moment of inertia now, let's adjust that way. Because there's a moment of inertia, the tensions are not the same, like in the Atwood machine that we saw before. Okay, so let's take a look at each of these objects. Here's M1, and here's the unbalanced force on it, T1. Okay, so that's it. To write the Newton's law equation here, T1 equals M1 times A. And then here is M2. This is M2 times G. And then this has T2 pulling up on it. Okay. And so this is, it's accelerating that way, so we're going to make this positive. M2G minus T2 equals M2A. Right, and then we'll solve this for T2. T2 is M2G minus M2A. Okay. And now we can look at the pulley. Here's the pulley. It's got T2 going that way and T1 going this way. Those are the two torques on the pulley. And so tau equals I alpha. And what are the torques? T2 times R. And let's see. Since we're going to change the positive negative direction here because of direction this is accelerating, right? It's accelerating this way, so we're going to say this is the positive direction. So I'm going to say T2R minus T1R. Right, those are the torques. This is the force times the radius. Equals I. And then alpha is A over R. That same acceleration that we have in those. So now what I'm going to do is I'm going to take this and plug it in here, and this and plug it in there, and see what that gets me. Okay. So T2 is M2G minus M2A, that times R, minus T1, which is M1A times R, equals I over R times A. Okay. Let's see. Okay. Then I can factor out. So now I have to get everything with A over to one side. So this is going to be M2G R minus M2A R minus M1A R equals I over R times A. All right, so let me do this. M2G R equals I over R A plus M2AR plus M1AR. I factor out A, then I'm going to divide over here. Since I have all of these R's, but actually what I'm going to do is I'm going to divide by this R and get rid of these R's and make this R squared. So in my numerator here, I'm just going to have M2G. I'm going to move this up here now. So now I'm going to have M2G over everything here except for the A's, right? I factor out A. So this is going to be M2 plus M1 plus I over R squared equals A. And that looks a lot like the modified Atwood's machine from before, except again, I have the mass equivalent, we can call it, of the pulley here, right? I over R squared. I is in the form of kilograms times meters squared, so this gives me kilograms. It's a mass equivalent. That's the acceleration. Now the tensions are two different things, right? I have two different tensions. And the way that I get those is simply I take this and I plug them in here and here. I take A and I plug it in, which is going to be a little messy. Actually, plug A in here. It'll be better. Okay. So then T1 is M1, M2, G over M2 plus M1 plus I over R squared. So this is A, this is T1. And then T2 is equal to M2G minus, and then M2 times A, and this is A, so it'll be M2 squared G over M2 plus M1 plus I over R squared. And then we can do some kind of crazy simplification stuff if we really want. I can take this, right, and make two fractions here. So let's try that. T2 equals M2 squared G plus M2 M1G plus I M2G over R squared. Right, so I made this into a fraction. I multiplied this by that. Minus M2 squared G all over M1 plus M2 plus I over R squared. And then this and this cancel out. And I'm left with, this is really bad use of board space, by the way. If you're a teacher, don't take notes on how to do this. So T2 is M2 M1G plus I M2, actually let's take G out, I m2 over r squared all over m1 plus m2 plus I over r squared times g. So that's T2. Really messy. And now, one of these crazy problems that someone dreamed up. We have a sphere with a string wrapped around it. The string is passing over a pulley, and then there's a weight here. They let the weight go, and the string unwinds. The sphere starts spinning, the disc is spinning, the pulley is spinning. And so we want to know what is the speed of the suspended mass when it has fallen 82 centimeters. This is a GAPSI problem. But the thing is, I start off with potential energy. So here's the gravitational potential energy. Here's my datum, which is 82 centimeters below the place it begins. But at the end, what do I have? Kinetic energy. But I've got kinetic energy of three objects. The kinetic energy of this, and of this. So when I write the GAPSI equation, it's mgh, I'm using little m for this guy. And then at the end, I'm going to have kinetic energy. How much kinetic energy? Well, I'm going to have the kinetic energy of this, which is 1/2 mv squared, plus the kinetic energy of the pulley, so that's plus 1/2 I of the pulley, omega of the pulley squared, plus 1/2 I of the sphere times the angular velocity of the sphere squared. Now, because of the string is taut, right? It's not stretching. The speed of this is going to be the tangential speed of the disc, the pulley, and the sphere. And so, as a result, omega is v over r. Well, big R for the sphere and little r for the pulley. I can plug that in here. So this is 1/2 mv squared plus 1/2 I of the pulley times v over little r, because that's the pulley, squared, plus 1/2 I of the sphere, the mass of the sphere, or the moment of inertia of the sphere, is, and it's a solid sphere. Oh no, it's a spherical shell. So then it's we'll leave it for now. And then this is v over big R squared. See how far we can get with that. Equals mgh. Now I factor out v squared, and then I'll be left with this. This is going to be mgh. Let's do this. Multiply by 2 as well. 2 over mgh. So now I'm going to have, this is just going to be m plus moment of inertia of the pulley over the radius of the pulley squared plus the moment of inertia of the sphere over the radius of the sphere squared. And again, the spherical shell is 2/3 mr squared. So this is v squared. So now I have 2 mgh over m plus mass of the pulley over the radius squared plus this is 2/3 mr squared over r squared. So the r squareds cancel out. They're just left with 2/3 m. And now I believe that we can just plug in numbers because we have this is just so then omega, or rather v, will be the square root of this whole thing. So that's going to be 2 times 0.6 times 9.8. I did use 9.8 this time. times 0.82, which is the height that it falls, over the mass, which is 4.5, plus 3 times 10 to the third over 0.5 squared, plus, plus 0.8, because the that's 0.6. So this is the mass of the of this guy. So that's 2/3. That's the mass of the sphere. And when you do that, you should get 1.417 meters per second. And that's it. Nice work. Thank you. Yeah, I guess you're not so bad after all.